Hey, it's Mr. Shrum, and I'm going to walk through the periodic trends of the elements and help you with the activities. And this tutorial is all about how to see the trends and use the periodic table to help you understand the properties and the structure of these elements. And we'll get into the electron configurations. Consider a situation where several balls are rolling down the hill. The balls will want to stay in a stable place where they have the least amount of potential energy. And that is at the bottom of the slope. So you see how they want to go towards this bottom slope area, whether they're up here and then they go up here and like, oh, and then they fall back down to this area. And eventually they settle at that bottom point where they have little potential energy. Electrons arrange themselves in a similar way. Electrons want to be in a place with the least amount of potential energy, and that way they are stable. They naturally occupy the positions where they have the least potential energy. This is an orbital diagram, and you fill up electrons starting at this level here. 1s, and then 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. And as you go up in the levels of the orbitals, the more energy they are. So they want to start out here in the most stable, least potential energy. Scientists use these orbital diagrams to represent the arrangement of electrons, and each box is an orbital. And each group of boxes represents a sub-level. And we've talked about this before: the S sublevel, the P sublevel, the D sublevel, and the F. Okay. And for example, we have silicon here. Its atomic number is 14, so it has 14 electrons. Okay, let's fill in the boxes. It starts off with 1s, since it has the least energy. One arrow goes this way, the other arrow goes the opposite way. Same goes for 2s. And then 3p, we have to follow certain rules. You'll add one arrow going this way to each box. And then once you fill up all these boxes in the P level, the 2p level, you'll add arrows the other way as well with opposite spin. So you do that with 3s, bam, bam, and then same thing. But we only have 14, so we can't fill up all of 3p. And that's what we end up with. And you can see the explanation on this side of the screen as well. Pause the video, read through that. Here's an example again. We do 1, 2, 1, 2, 1, 1, 1, 2, 2, 2, 1, 2, 1, 2, 1, 1. Writing electron configurations. So we take this information and then write it out as in 1s2, there's 2 in the 1s, 2s2, there's 2 there, 2, 4, 6. There are 6 in a P level if it's all filled up. 1, 2 for 3s, and then 3p only has 4. So 1, 2, 3, and then 4. Okay. Okay. And this picture helps you remember which level you need to fill in first. So you start from the top right and then drag the arrow towards the bottom left. And then as you cross these off, that will show you the correct order. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. So here's, let's do an example for arsenic. Arsenic has 33 electrons. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 plus 6, 18, plus 10, 28, 30, 33 for arsenic. So it goes all the way up to 4p3. Oh, whoops, you saw it. The periodic table and electron configurations, you'll notice that the S's are here in the main group, the P's are on the other side near the nonmetals, and then we have the 3D block here, and then the F block for the inner transition metals. D block is transition metals, F block inner transition metals. Here's more. This was a weird way to write this out, but it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Okay, and we found that out by looking at this order here. Okay, so remember this, write it down, take a picture, you'll be fine. Noble gas notation helps us not write out all of these numbers, which is great. You can just say, we'll start off here and then write in the information up to this point. So you don't have to write in all this extra stuff. So for example, this is lead, right? 1s2, 2s2, 2p6, and so on, all the way to 6p2. Xenon is the noble gas right before that period. So you can just say xenon and then start off 6s2, 4f14, 5d10, 6p2. So it shortens everything and makes it a lot easier to write out. Here's more matching. Zinc is there, 3d10. Iron, you can use the noble gas notation. You can do the same for tin. And then chlorine is easy enough where you don't have to do that. These electron configurations only are used to represent the positions of electrons within the atom. The order in which the sublevels are listed can vary. So you may see things like 6s2, 4f14, 5d10, 6p2. But you can also write it 4f14, 5d10, 6s2, 6p2. Whatever is more sensible to you, I'd stick with one and then just go with that, because it can confuse people to just jump back and forth. And now we have the lesson activity, exceptional electron configurations. Review the electron configurations of the elements in period 3 from sodium to argon. What do you observe? After the 3s sublevel is filled with 2 electrons, each additional electron goes into the 3 sublevel, the 3p sublevel. Yes, that is true. Each element's electron configuration has a noble gas core with 2 electrons in the next s sublevel. Yes, so you're realizing that the configuration have patterns, okay? In group 2, you're moving from beryllium to radium, and we'll show you what that means exactly if we can get it pulled up. Okay, so for the first question, we were moving across here from period 3, period 1, 2, 3, from sodium to argon. And if you look here, the electron configuration is 3s1, 3s2 for magnesium, 3s2, 3p1, 3s2, 3p2, 3s2, 3p3, 3p4, 3p5, 3p6. Easy peasy, okay? Now we're gonna look at beryllium and going down to radium here. So we have 2s2, helium 2s2, and then neon 3s2. So it'll just have a noble gas and then s2, depending on the level. See? Cool. Not hard to figure out. See the trends. So that's why that answer is correct. Part C. Review the electron configuration of the elements in period 4. Select all the elements in period 4 that have electron configurations different from what the rules predict they should have. We have chromium and copper. If you look at it, we go from 4s2 or 4s1, 4s2, 3d1, 4s2, 3d2, 3d3, 3d5. You see how it jumps when we get to chromium? It's kind of weird. Then we're going back. 3d6, 3d7, 3d8, 3d10. So it jumps again. So chromium and copper behave differently than the rules. Which of these elements from the D block have electron configurations that don't fit the expected pattern? Ruthenium, gold, and silver. And I'll show you. Gold, you see how 4d10, 4d10, 5s1, and then, okay, so silver, acting weird. We go from 4f14, 5d9 to filling up that D interval. So we got silver, gold, and ruthenium too. We go from 45, 5s2 to 47. So strange. These guys do not play by the rules. And here are other ones that don't fit. A lot of the D block acts a bit funky. Electrons in the 5s sublevel and the 4d sublevel have very similar amounts of energy. And this is shows the main groups and the transition metals and the inner transition elements. You'll notice that some elements have exceptions to the electron configuration rules. Select all the blocks that contain elements with exceptions. It's F and D. Those guys behave differently than the rest. Now we're going to look at the trends, okay? Remember, we have metals on this side of the table, non-metals here, metalloids, or kind of a bit of both in between. Here we have atomic radius, how big the atom's center to the edge is. And it increases to the left and down. Increases to the left and down. And it'll show you why that happens. Atoms that have lost or gained electrons are called ions. This shows the trend in ionic radius. It goes up to the left and down. It increases going left and down, same thing. So you have atomic radius and then ion when it becomes a charged ion. That radius increases the same way. It says arrange the elements in order of increasing atomic radii. oxygen, selenium, calcium, barium. So here's oxygen, selenium, calcium, and barium. Okay. So you're starting off at oxygen, and then you're moving down to the left and down. Okay, they're following that trend. The octet rule, okay. The octet rule will help us understand what are these ions and electron configurations trying to be, okay. Octet, they want 8 in that outer sublevel. That is very stable. Sodium, +1 ion charge. Here's the electron configuration. Neutral atom with similar electron configuration. And that means the octet rule, they're trying to have an outer shell like a noble gas, because noble gases are stable, okay? Sodium is trying to lose an electron to become like a noble gas, like neon. Magnesium, +2 ion charge, trying to be like neon as well. Oxygen, -2 charge, so it's trying to gain electrons to become like neon, okay? Metals want to lose electrons because they're so reactive, they just want to lose 1 or 2. Oxygen and these non-metals would like to gain 1 or 2 electrons and become stable. Here's the increasing reactivity in metals. So it's the same trend to the left and downward. Okay. Sodium is more reactive than aluminum is. Okay. For example, this video, you should go and watch this and see how reactive some of these elements are. Some of these metals are. Okay. So these ones are very reactive, and it'll show you how reactive they are in comparison with one another too. So this is wait. Yeah, this is lithium, first of all. They need to store them in oil, I believe, to stop the reactivity. And they're very soft. You'd expect metals to be, hard, but they're very soft in this case. There's sodium, even easier to cut, and then the surface discolors as it reacts with the air around it, the oxygen. Here we have potassium, and it even reacts faster. So you can see the reactivity is going up. Same thing if you put them in water. Lithium floats and kind of just slowly reacts with it, causing those fizzing bubbles. That means there's gas being produced, right? You can use fire to show you. There's actually an audible pop. Here, I'll play it.
Universal indicator. Water to form lithium hydroxide and hydrogen. So how does sodium react? Again, it floats on the water and fizzes. The gas produced is hydrogen. And the solution is alkaline. When sodium reacts with water, sodium hydroxide and hydrogen are formed. Sodium is more reactive than lithium. It's below lithium in the periodic table. Potassium is below sodium. So how do you expect potassium to behave? Potassium is definitely more reactive than sodium and lithium. It reacts immediately, and the hydrogen produced ignites on its own. Universal indicator goes blue. Potassium reacts with water to form potassium hydroxide and hydrogen. Rubidium and cesium are elements which lie below potassium in the periodic table. How would you expect rubidium and cesium to react with water?
Well, we'd expect them to be more reactive. You saw how potassium was a lot more reactive than some of the other ones, violently so. All right, so the trend for reactivity in metals is to the left and down. The reactivity in nonmetals, so this group up here, or to the right of the table, the nonmetals are more reactive if you go right and upward, so the opposite of the metals. The most reactive metal is down here and to the left. The most reactive nonmetal is up here and to the right. For example, here's magnesium, calcium, potassium, rubidium. Magnesium, calcium is more reactive than magnesium, potassium is more reactive than calcium, and rubidium is more reactive than potassium. Ionization energy is the amount of energy required to actually take away an electron from an atom. In small atoms, the valence electrons are very close to the nucleus and strongly attracted to it. It takes more energy to remove them. Small atoms have higher ionization energies. Elements that lose electrons form positive ions. So the elements that easily react to form positive ions are the ones with the least ionization energy. Reactivity increases towards the bottom left of the periodic table. So ionization energy is lowest toward the bottom left of the periodic table. It increases towards the top right of the table. So ionization energy up and to the right is increasing in ionization energy. Here's the sequence for this: gallium, phosphorus, chlorine, and then fluorine. Okay, increasing ionization energy. Gallium is lower, or well, here, I'll show you. Oh, just kidding. Gallium, show me a gallium. Gallium's right here. And then you make your way to fluorine. So more reactive upwards, and ionization energy increases upward and to the right. Okay. Easy, easy. Electronegativity follows the same increasing trend, up and to the right. Electronegativity is a measure of how strongly the atoms of an element attract their valence electrons. So you see how it's tied into ionization energy. The electronegativities of two atoms in a chemical bond may attract the same electrons. And this indicates how much attraction each of them has for the electrons in the bond. Because the noble gases don't typically form compounds, the electronegativity values are largely unknown. We just don't know. They just don't do that in nature all that often, so we're not sure. Large atoms have electrons and they're further away from the nucleus. So the attraction of the valence electrons in large atoms is weaker than the attraction in small atoms. Makes sense. Here's the sequence for that. Electronegativity to practice with that. Potassium, aluminum, boron, and then nitrogen has the most electronegativity. And that's it for trends. The best way to study this or remember is to draw or take notes, study the arrows, and then remember and go back over the reasons that are underlying those trends. All right. Remember, the size of the atoms can affect things. The position and the electron configuration of the electrons can change the way things are for trends. And yeah, if I can explain that more for people, let me know, and we can explain that in more detail. But until next time, have a good one, and I will see you all next time.